All right, so welcome everyone to this Monash Cybersecurity Seminar. Today we are really delighted to be having a face-to-face or in-person seminar for the first time. And we are also very happy to welcome Joseph Bonneau, who is an associate professor at the University of Melbourne. And he works on applied cryptography and computer security. And he is a co-author of the textbook Bitcoin and Cryptocurrency Technologies. And he got his PhD from Cambridge University and completed postdoctoral fellowships at Princeton and Stanford universities. And today, Joseph will talk to us about new applications of zero-knowledge proofs. Thank you, Joseph. Over to you.
Thanks so much for having me. It's great to be here. I've now spent, so I moved to Melbourne Uni in the middle of this year, and I guess I've now spent more days on campus at Monash than at Melbourne Uni. Basically nothing seems to be happening in person, so it's great to see so many people. It's probably also the first seminar I've done in about 2 years. So I'm just going to talk about a couple of things I've been working on in the last year. So I've been working on applications of zero-knowledge proofs, mostly outside of the blockchain space for a change. At least that's what I'll talk about today. So really, I guess I'll be talking about 3 different papers that I've been working on. And I'll try to mostly talk about what the application is and why I think it's interesting. And let's see, at least 2 of the papers are online, so you can read them. The third one, not online yet, but I can send it. So I'll try to keep it high level and not go into a lot of detail about zero-knowledge proofs. But hopefully, I guess, the cybersecurity seminar, you've heard of or seen zero-knowledge proofs before. You've probably seen people try to explain them by analogy with the Where's Waldo book or with a cave and showing 2 different ways. But essentially they allow a prover to prove that they know some secret with some property, like they know how to solve a Sudoku puzzle. So you can provide an efficient proof of that, the fact that you know the solution without actually having to reveal it. That should convince some verifier. So the proof basically makes this claim that you know some secret information with some special property, and the verifier has some efficient algorithm that they can run to verify this. So this has been a really active area. I'm sure people have heard about all the progress in SNARKs and new schemes coming out all the time. So it's been a really, really exciting area. I mean, basically people have been working on this since the 80s. We've known for a long time that zero-knowledge proofs are possible for any NP statement. But in the last 10 years, we've actually seen people start to use them for real things. And there are a lot better tools now. So there are compilers to produce these things where you can specify in a, not quite as simple as specifying it in C code or a programming language, but in a higher level language, you can specify the statement that you're trying to prove, and then compilers will produce a zero-knowledge proof system for you. So you've probably heard about these in the blockchain space, which is kind of the killer application that I think has really gotten zero-knowledge proofs into practice. Sort of for 2 reasons. The obvious one is privacy. You'd like to be able to prove that transactions on a blockchain are correct without revealing how much is being paid or who's being paid. Recently, people are even trying to do smart contracts and complicated calculations in zero knowledge so that you don't have to reveal what's happening on the blockchain. So we've seen some successful projects like Zcash and Monero that use zero-knowledge proofs for privacy. And we've also seen a lot of projects that use the same technology just for efficiency, not even necessarily for privacy. So it actually turns out, if we go back to this picture, the fact that you're proving something about a big statement and that the verification is really efficient, it turns out that's really useful in some cases, even if there's no private input. So you reveal exactly what you're trying to prove. It's called verifiable computation then. But turns out, I mean, this is the difference between a snark and a ZK snark. And the terms are used so interchangeably now that people just say snarks to refer to the whole thing, whether or not there's a zero knowledge aspect to it. It's interesting that the techniques are mostly the same. So there's some other blockchain projects that use use the same tools just to get efficiency, just to prove that a lot of transactions are all correct, and then produce a short proof on the blockchain, rather than having to prove every individual transaction is correct. The blockchain space is still driving a lot of the advances in zero knowledge. But I've been working on other applications that you can use the same technology for, as have a lot of other people. So there's a large program being run by DARPA, which is a US government funding agency that tries to do big moonshot type research. So they've been running this $20 or $30 million research program over the last couple of years that I was lucky to get some funding from. And basically the one requirement they said was no blockchain applications. So it was funny in some of the PI meetings when people were sort of obviously wanting to talk about a blockchain application, but there was almost a taboo against saying the word blockchain because people didn't want to violate the rule that DARPA said very clearly they didn't want blockchain applications. But I think it's been a really good program because it's encouraged myself and a lot of other people to think about what we could do outside of the blockchain space. So like I said, I'm just going to give a high-level overview of 3 projects that came out of this work. The first one that I worked on with a bunch of colleagues when I was at NYU, ongoing work, I guess, is called Zero Knowledge Middle Boxes. And the goal of this project is that we want to allow users to communicate on some network using encryption, using something like TLS, and still be able to enforce some use policies for the network. And zero knowledge proofs will be the tool to get there. So there's a lot of applications that network middle boxes perform today. Probably the most widespread one is filtering. So on a lot of networks, this middle box, you can really think of it as like the wireless router that you connect to. And every DNS query that you make, it's going to check against some block list. So there's going to be a list of domains that you're not allowed to visit on this network. So you can think of that as being like adult content websites if you're at school or on an airplane or something where that's not considered appropriate. So the middle box is just going to check if the domain that you're trying to resolve is blocked. And if it's not, then it will allow your query to actually go to some remote DNS resolver. So this has been widespread for decades, and millions of networks do this. It's easy to say it would be better if there was just no filtering. The internet should be free and people should go wherever they want. But I think there are a lot of applications where people would agree that some filtering is reasonable. And in fact, for school networks in the US, it's a legal requirement. So they have no choice. It's written into law that they have to actually filter. They have to filter adult content at school networks in the US if they have students who are below 18. And there's a lot of other applications around the world where filtering is in some sense required. The parental controls one was actually interesting because when we got into this work, I hadn't thought about it that much, but it turns out there's tons and tons of parents who run a filtered home router who have kids in the home who want to limit what their kids are doing on the network. So kind of the trend the last couple of years is that encrypted DNS has been rolling out. So traditionally DNS was just a clear text protocol with no security, and anybody observing the network could look at all the domains you're querying. And there have been a bunch of standards proposed in the last 5 years that are now deployed, and they are implemented in your browser that actually encrypt all of your DNS traffic. So there's a whole stack of different protocols for doing this with slightly different properties. The differences don't really matter for this talk specifically, except to say that this is a real thing, and Firefox actually implemented it by default, which is good because it gives users more privacy for their DNS queries. Kind of a similar trend is that a lot more people use a non-default DNS resolver now. So just a couple that are popular that you may have seen. So all these DNS resolvers support all the encrypted DNS protocols. So you can switch to Cloudflare, Google DNS, and you can encrypt all of your queries. Like I said, the browsers, at least Firefox and Chrome, support this now. Firefox actually supports it by default, but there's kind of a caveat to that default that I'll get to in a second. But the encryption is a problem for the filtering example, because the middle box, by design, we don't want them to be able to tell what domain you're querying for privacy. But that means that they can't check to see if it's on some block list or not. So there's kind of I guess what the networking people call a tussle between values, where the clients want privacy and the network administrator wants to enforce some filtering policy, or they may have to enforce some filtering policy. So as a result, like I said, Mozilla had to build in kind of an uncomfortable caveat. So there's actually a way, if you run a network, you can tell all the Firefox browsers on that network not to use encrypted DNS, which is a bit weird. There's a special domain that you can see there. And basically, if you return anything for that domain on the default DNS resolver for the network, then the Firefox browser says, okay, I'm not supposed to use encrypted DNS on this network. So a lot of people were really unhappy about this trade-off. The reason that it was made is that basically, Mozilla was told if you push encrypted DNS by default, every school in the United States is going to have to uninstall Firefox from every computer in the library because they won't be able to enforce filtering. So this is not a very satisfying trade-off. It's kind of all or nothing. Either you get privacy or the network gets to enforce its policy. There have been a couple of lines of work previously to try to resolve this problem. The simplest one actually is just use trusted hardware. So you have basically some filtering logic built into the router that runs an SGX or a trusted enclave, and you disclose your TLS keys that are used for the encrypted DNS to this enclave on the router. And you say, okay, well, they still get to see my traffic, but it's only some enclave, and you can get an attestation of what code is running. And there's also been some cryptographic work, but all the cryptographic work previously requires changing TLS. So not using TLS as it is, but using special encryption tools that allow you to do things like searchable encryption, where you can sort of reason about if the encrypted query is on some block list or not. And that is a whole bunch of problems. All the work that we've done on TLS is sort of out the window at that point. You have to reprove that it's secure. You have to re-implement TLS, and you also have to change every server in the world. So our solution obviously is to use zero-knowledge proofs. So the client has to be aware of the block list now, although I'll talk about how you can relax that assumption. And then when you make an encrypted DNS query, you attach a zero-knowledge proof that says, obviously the decryption of this encrypted query, and you prove in zero-knowledge that it's not one of the block domains. So the middle box runs the zero-knowledge verification algorithm, and the only thing that they learn is that this is a query to some domain that's not on the block list. So they don't learn what domain you're actually querying, they just learn that it's not a block domain. Which is kind of what we want. It's the best privacy that you could achieve. And then as long as that proof verifies, they'll forward your query to the DNS resolver. Our goal, obviously, privacy, clients should be able to keep as much privacy as possible, which is that the network doesn't learn anything except that, you've satisfied the policy. We also really wanted compatibility. So we assume that you can change clients, so you could add some code to the browser, but that you can't go and change every TLS server in the world. And that we got to that by talking with the browser makers, and they said in practice it's much easier to change browsers than to change servers. Most modern browsers now update every month, and most users are pretty close to up to date. Whereas TLS servers, it's still, there's something like every 3 years is like the median point at which they get updated. So that was our goal, is basically to enable this privacy plus policy enforcement without having to change TLS and without having to change anything about TLS servers. So in fact, in our system, the server doesn't even know that this zero-knowledge protocol is happening. And then, within that, we want sort of as much flexibility and efficiency as possible. So there's a lot of ways around this. If sometimes people object and they say, well, what if you don't use DNS? What if you use a different protocol? Or what if you route it through some inner encryption layer? And the answer is, yeah, if the client is working to get around this, they'll be able to get around it. Which is a bit of a strange assumption for security work. If we say, yeah, like, we want really motivated clients to be able to get around this. We sort of got there on one hand because it's very difficult to prevent. If the client is just trying to get some information about, the IP address for a domain, right? They can get it out of band. There's lots of ways they can get it. It could always be just encoded in text on a website or something like that. But we also sort of want filtering and not censorship. And these aren't maybe precisely technically defined, but a censorship system is one in which it's designed so that nobody can get around it. And if you try to get around it, you might be punished, which is something like a big steel wall that's designed so it's impossible to get over. Whereas filtering, it's a bit more of a social convention. The goal is that most people won't get around it. It will keep most people sort of in the place they're supposed to be, without actually like being a real threat to people's freedom. So hopefully we're in the filtering zone and not there's kind of a third solution where you just tell people this is a school network, so be responsible and don't access any adult pages with no enforcement. So hopefully we're at some happy middle ground between really limiting people's freedom and just trusting everybody to behave. So like I said, since this is a chopped up talk with a couple of different ideas, I'm not going to go too far into how we actually implement this. I guess I'll just say that the block list is distributed as a big Merkle tree. So the client provides a non-inclusion proof. So it's a sorted Merkle tree. So it's very efficient to prove that a domain that you're looking up is not in that Merkle tree. And the full circuit, in addition to the non-inclusion proof, is the really cheap part. The expensive part is actually proving that the decryption of some TLS encrypted packet. So that's where probably 90% of the engineering work went here. I could have said in the beginning when I was talking about zero-knowledge proofs that we have all these great tools now and people are using them for lots of exciting things. Actually getting them to run efficiently is a bit more of an art than a science right now. So almost everything that you want to do using SNARKs, you have to sort of hand optimize to get the performance to be reasonable, and usually think really careful about it. So there's a lot of tricks in the paper about how you can do this more efficiently and not have to do all the Diffie-Hellman operations in the circuit. So we're able to avoid that by taking advantage of hashes of keys that are committed to in the transcripts, and then you can just prove that the hash preimage, and it ends up being a lot more efficient. But you do have to prove things about the TLS schedule. If you've never looked at the TLS schedule for TLS 1.3, it's this really, really complicated thing where dozens of things are derived and hashed. So that all got implemented in the circuit. So we implemented it all. The most expensive part is just doing all the SHA-256 hashing that's in the key schedule. Everything with SNARKs, well, at least with like Roth 16 SNARKs, the most popular ones, the proofs are always small, the verification time is always efficient. So proving time is almost always the thing that you have to worry about. So our kind of initial unoptimized implementation, the proving time is 20 seconds. So if you do one DNS query, you have to do 20 seconds of work to prove that it's not on the block list. So 20 seconds isn't great. Obviously, if you added 20 seconds of latency to every web page you tried to open, people wouldn't use the system. Like I said, it's almost all due to that key schedule. But it turns out we've actually, since putting the paper up, we've improved it a little bit. And the simplest improvement actually is just that you can do one initial proof to set up a connection with the DNS resolver. And then every subsequent query you make is a lot shorter. And you can actually pre-compute these things too. So the best story for latency is that it takes about 6 seconds to compute a proof for each packet you want to send. But in a real implementation, you could pre-compute those. And then when the user actually types in a domain they want to go to, you sort of have one ready to go. So you shouldn't actually have to add any latency to the user. But you do have to sort of eat that cost in the background. So like I said, it shouldn't affect latency. You know, this is ongoing work. Like I said, we're trying to, should say that the students are hard at work trying to make this more efficient. People have asked about, you know, if you could do this where the client doesn't have to download the whole block list. So the current model, when the client joins a network, they have to download a big list of all the domains they're not supposed to go to. And it turns out that you can. So we have a protocol that adds an extra step because you have to do a private set intersection between the domain you're trying to look up and the block list, which the middle box has. But it's possible to do that. And it's possible to take this zero-knowledge middle box's idea and do other applications besides filtering. So there's a lot of other potential use cases of things that middle boxes try to enforce on encrypted traffic. Yeah, so that paper's online, and would encourage you to check it out. So that was project 1 I've been working on. Project 2, you might notice there may be a font change or two. Oh yeah, if you have a question on. Yeah, go ask a question.
So I have some questions for the first work. So the first one, I guess probably you mentioned in the last slides, you talk about you want to support private block list, which means that right now you don't preserve the root privacy at the moment, right? The middle box see all the plain text.
No. This is about the client learning the block list.
Okay.
So what the client learns, this is the list of all domains that you're not allowed to visit on this network, which is sort of, it's arguable if you ever really have privacy for it, because the client can always just, if you're implementing blocking, the client can always try to go to domains and see if they get there or not. So they can always learn the block list kind of piece by trial and error. But in the more efficient system, the client just downloads the entire list of places they're not allowed to go.
Yes. I'm asking because because we are also doing this line of research, but not on the zero-knowledge proof, but on the privacy preserving network function. Because right now you're talking about the DNS filtering, which is the function is very simple, but actually the middle box can support like, for example, packet payload inspection. So then they may have some requirements on the root privacy. So otherwise the client can bypass the detection somehow. Yeah, so that's why I'm just wondering about this question, whether your work can be future extended to support root privacy.
Yeah, so in principle you could do secure multi-party computation to enforce any private policy. That's probably going to be pretty inefficient in practice. So one of the reasons that we kind of focused on the DNS application is that it's very simple, so it works well with the zero knowledge. And probably for more general, like you said, like packet inspection stuff, the overhead of this might be too much today, and the privacy aspect might be a problem.
Yes, exactly. And another question is probably is a kind of comment, because you mentioned that blind box and the in-bug, they have some weakness, right? So they somehow try to modify the TLS. So, but actually, I think they actually they still keep the TLS connection, but they deploy their protocol. Like for example, they somehow, because as you mentioned, they adopt censorship encryption. They just attach censorship encryption protocol on top of the TLS. They are separated, protocols. I guess this is quite similar to your work because the TLS will not be changed, but your protocol is still like running in parallel with the TLS.
Yeah, so I think that the two main advantages of this approach are you don't have to change the TLS server. So their system requires you change, the client and server both have to change. But also, there have been like some attacks certainly on like blind box, right? Where stuff gets leaked by the searchable encryption. So I think we have like a much stronger security guarantee that nothing's leaked, at least, in line with how secure the zero knowledge property of your proof system is.
Sure.
Yeah.
Thanks.
Yeah, sure.
So I have probably two questions. First one is about the overhead on Middlebox now. So I think you put a burden on Middlebox rather than the servers because you were saying, we don't want to change the servers.
It's pretty light. It's like I said, the SNARK verification is pretty cheap. It's not nothing though. So yeah, like if you have like millions of client connections, then it would definitely add some overhead to the middle box.
And I think you also mentioned that has to have a memory or a storage as well in the amortized version.
That's just clients.
Oh, that's the client.
Yeah.
Because I saw in one of your slides, it's this one. Store some state.
Oh yeah. Yeah, it's like linear in the number of clients. So it's pretty small. They basically just have to store like the equivalent of one proof. But yeah, it does.
And then the second question is about like asking the users to be nice to the system.
Yeah.
So does that address the legal needs, for example, in the
good question. Yeah. No, it turns out it doesn't. So the way the law has been interpreted, they have to have a technical filtering mechanism. There's a whole separate conversation about. It's a weird setup where the school might not actually, the network admin might not care that much. They just feel like they have to do something so that they complied with the law. So yeah, it's unclear exactly like how motivated they are to really enforce it strongly, but no, you can't just tell the students, not to visit certain sites.
Hi, so thanks for the talk. And I just want to ask, because you talk about censorship and filtering, I just see whether this current design can ensure that, because you're also using some Merkle tree, right? So how to ensure that the data set is distributed by a trusted authority and it's not modified by a specified party. So for example, as you mentioned, you say the school should have some rules filtering, right? But how to ensure that the school use the legitimate rule set instead of some modified one?
That's a good question. I mean, you would get it like through like DHCP basically. So when you join the network, right, like they give you some network setup info. Yeah, I hadn't thought about an attack where someone modifies that to try and convince you to use like a bigger.
So it's still possible because, for example, if somehow like, so, Apple also have their rule set. So they just have a controversial system. Say they want to inspect those users' content with exploit the children.
Mm-hmm.
So, however, if Apple moves to the other countries and the other country wants to apply some censorship, they enforce Apple to add those in their rule set. So this system will not be only used to detect those exploit children content. Yeah, so there will be a difference. So how to,
I guess, are you asking about like a network enforcing, too broad of a list, or somebody modifying what the network meant to enforce?
Yeah. So like you have a central authority to distribute, but is it possible that modified by the other party? So how to avoid this kind of scenario?
Yeah, I think in practice, I mean, if you were using a different Merkle root than the network was expecting, then all of your proofs would fail. Because like one of the inputs to the proof is the Merkle root. So if you had a different one, like all your traffic would be dropped by the middle blocks. So like I think I hadn't thought about that before. I think it would be okay. I think if you tricked you're basically talking about like tricking the user into using a different Merkle root. I think that all the proofs would be considered invalid by the middle box, and they would block all your traffic. So you'd sort of figure it out.
Okay.
Yeah.
Yeah.
But yeah, I mean, there's a separate question about, we've thought about this, and it's a tough question. Like, if this is all built and deployed, would it encourage more people to block because they could say, oh, we can do filtering or censorship and it's privacy preserving? And not clear. I think like the most aggressive regimes that censor don't really care about the user's privacy to begin with, so they probably wouldn't be motivated to use this system. But yeah, it's a tough question.
Hey Joe, I just wonder if there is any kind of such solutions being already deployed. Let's say in the States, whether those colleges or schools would already use some sort of these type of applications for filtering.
Yeah, no, they're well, I mean, they're definitely filtering. They're all doing filtering today, but yeah, basically none of the current filtering systems work with encrypted DNS. So that's why Mozilla built in the thing to just block it.
But,
so,
I mean, the reason I'm asking this question is that it seems to me all the tools for breaking the censorship would also work here, right? To break the filtering.
Yeah, totally. Yeah.
If I'm a student or if I'm a child of a parent who wants to use the parental control, I would definitely Google to search possible VPNs or tools to get around, right? So
yeah.
I would be quite curious to see how those tools would change the behavior of the
Right.
users. That
So,
seems to be quite interesting.
I think all those evasion strategies work today, and they would still work with zero-knowledge middle boxes. So this proposal is kind of neutral as far as evasion goes. Like all those things, right? Kids today figure out how to use a VPN or an alternate DNS server to get around what their parents are trying to do, and like the same set of solutions would work. So I guess that's probably, we felt comfortable with that we're not changing the difficulty. Yeah.
Yeah, can I ask? So when you do this snark, are you representing this whole algorithm as a Boolean circuit, or is it a mixture of Boolean and arithmetic, or how do you?
I'm not sure I understand. I mean, yeah, the whole thing gets compiled down into a circuit representation.
Okay. No, because you have a mixture of kind of symmetric key and public key primitives, no?
Yeah, but those all have to be represented in
So they're all represented in one way as this.
Yeah. So it's like, and there's a huge blow up. So like AES decryption turns into like, thousands of algebraic constraints. So,
Right.
yeah, so it's not super efficient. I mean, if you wanted to read, like, there's kind of a growing field of like circuit friendly crypto, which we actually do use for the Merkle proof. So we don't use SHA-256 for the Merkle proof. We use Poseidon, which is a circuit friendly hash function, which has a very concise circuit representation, which is one of the reasons why that part of it ends up being really, really cheap. So yeah, if you could redesign TLS to use like Poseidon instead of SHA-256 and use a circuit-friendly encryption, then this would get way, way more efficient. So being stuck with TLS as it is means the circuit representation is not very efficient. But that was kind of like a design requirement for us.
Right. Okay. So do the public key operations also have a big?
So we don't. That was probably the biggest performance improvement, is that we don't do the public key operations.
Okay.
So yeah, there's
that hashing trick you mentioned. Or?
Yeah. So since there's you can prove basically that the Diffie-Hellman exchange happens and you agree on a master secret between the client and the server, but a hash of that master secret appears in the transcript. So rather than prove something about the Diffie-Hellman exchange in a circuit, it's much cheaper to just prove that you know the inverse of that, the pre-image of that hash function. So that's the way we do it. So that's good. Yeah, I mean, we implemented it doing the Diffie-Hellman, and it was like many minutes to prove.
Yeah, that makes sense.
So that's kind of like most of these applications. It's like there's multiple ways to do it, and you do a lot of like proof engineering to get it to sort of run efficiently.
Thanks.
Anybody else? Thanks so much for the questions. This is great. I'll probably, I don't know what time it is, but we'll probably reduce from 3 to 2. Okay. Okay. Well, let's see. So the 2 other projects I had were these client auditable registries and time-limited zero-knowledge proofs. Is there a strong preference from the audience for one or the other? Time-limited zero-knowledge proofs. Time-limited? Okay. All right. So I'll skip this section, but this is basically, if you've heard of key transparency or my work on conics, this is a lot to skip through. Basically, this project, the paper's online, and it allows us to do a key transparency server, so a server that lists every user and their public key, and allow clients to efficiently audit that their key hasn't changed, even if like a huge number of updates have happened. And it gives you privacy of the updates that have happened. So if I guess if you read the Conics 2015 paper, it's basically a reboot of that paper, but using SNARKs and making the whole thing much more efficient. Okay. I'm happy to talk about that more offline if people are interested. Just ask me about the key transparency project. So this project is maybe more out of the box because this is not just maybe an application of zero-knowledge proofs, but zero-knowledge proofs with a new property. And the property is that the proof is only convincing for a short period of time. So it's a bit of a stretch, but the analogy to the real world is if you sign something in disappearing ink, people can look at your signature for a while and be convinced, and then eventually it disappears and the signature is not there anymore. So obviously in the digital world, nothing, you can't rely on anything actually disappearing. So instead we build a proof system where the soundness disappears after time. And the way we do that is that there's essentially 2 algorithms to produce proofs. There's the traditional prove a true statement where you know a witness. And then there's a forgery that allows you to prove anything, but you have to do a slow computation to run the forgery algorithm. Okay, so you can prove a true statement efficiently if you know a witness. But if you don't know a witness or if the statement's false, you can still produce a proof through this forgery algorithm, but it's going to take you a long time. Specifically, you have to solve a verifiable delay function, which is another new crypto tool I've worked on. And it's an inherently sequential computation that takes T steps. And T can be chosen by, to be whatever you want, basically. And then we have the property that verifiers, there's an indistinguishability property about if a proof was produced by the genuine proof process or by forgery. And what that means is that if you think that a proof was computed quickly, then you're sure it's correct. But if you don't know how long it was taken to produce this proof, then it's not convincing anymore because it might be the result of this forgery process. So that's the high level idea of what we're trying to achieve. And I'll show you some applications. Okay, yeah, so if you're familiar with how proof systems are defined, it's basically the same. This is exactly how you would define any zero-knowledge proof system. We've just added this forge algorithm, which doesn't usually exist. And of course, the restriction is that the forgery is inefficient. So it takes T work, and you can set that to be as you want. So to make this non-interactive and kind of useful, you embed in the proof a beacon value, which is some value that everybody believes didn't exist before a given point in time. So it could be, the most recent Bitcoin block header. And then if you see a proof with a recent beacon value, you're convinced that the statement is actually true, because it must have been computed quickly after that recent value. But then far into the future, it will no longer be convincing, because you'll lose the notion that it was computed quickly. So that's the idea, is that the proof is only convincing for a limited window after that beacon value, and you can make that window as long as you want. Okay, so I'll show two applications of this. One of them is signatures for DKIM email. So this is, if you read Matt Green's blog, he's written a lot about this application. So DKIM is used to sign all email that gets sent now by major mail providers. It's not, there's one DKIM signature per domain. So like there's one DKIM key for all of Gmail, and every email that gets sent by Google, they sign using a DKIM key, and you can look up that DKIM key in the Google Mail Server DNS records. So the point of DKIM is really just an anti-spam measure. If you get incoming mail that claims to be from Gmail, you can check to see if it's been spoofed or not. But it had kind of this interesting unintentional property. So if you recognize that name, that was Hillary Clinton's campaign manager. So during the 2016 election, you may have heard about the alleged Russian hacking of Hillary Clinton's campaign and leaking of emails. What's interesting is that WikiLeaks actually used the DKIM signatures to authenticate that these were the real emails that were sent. So what was pointed out since then is that this isn't really what DKIM is for. It's only supposed to provide authenticity of the email for a very short period of time. And if your email gets hacked, 10 years later, you'd like to be able to deny it and say that's not really the real email. But these signatures provide long-lasting proof that that was actually the genuine email that you sent. So Matt Green's suggestion was that the DKIM server should just publish their DKIM key every 6 months or so, just publish their old private key and switch to a new one. And that way, it would invalidate the authenticity of all the old signatures. I should say, actually, Matt Green and some colleagues wrote a really nice paper at Usenix with a fancier system where you don't have to publish the key, you just publish like a tag that lets you forge, but yeah, similar to this. Using short-lived proofs, using our new construction, you can do this much more simply. You never have to change keys. You can use the same key forever, but you do a short-lived signature, which is like a special application of zero-knowledge proofs attached to every mail. And then it gives you the exact property that you want. If you see one of these signatures 10 years later, you don't know if it's real or not, because the person leaking the email might have just forged all of the signatures. So that was kind of our motivating application. And then another really nice application in voting was suggested to us. So there's a lot of cryptographic voting schemes that all have kind of a similar property where you submit your ballot to some voting machine. The voting machine encrypts it, and then it gives a zero-knowledge proof that the encrypted ballot corresponds to the ballot that you actually submit. Right, so you submit all the choices you have, and then you get an encryption of your ballot back with a proof that it was actually done correctly. And then later on, after the election, you check that your encrypted ballot is included in some bulletin board online, so you can see that your vote counted. The problem with voting protocols that always makes them really tricky is that you're not supposed to be able to sell your vote to somebody else or prove how you voted. There's a couple of ways around this. There's one really famous way actually is that you just get the proof is shown to you like behind glass so that you can't actually take it with you. But with short-lived proofs, it's really easy. You just, the voting machine gives you a short-lived proof that your ballot was actually encrypted correctly. And maybe the time parameter is set so it takes like a minute to forge this proof. So, when you see it in the voting booth, you're convinced that the encryption was actually correct. But by the time you leave the voting booth and try to show it to somebody else, they won't be convinced by this proof because you could have forged it in the time, since you left the voting booth. So kind of a nice, really simple application where you use short-lived proofs and then you get this deniability property that you want. I guess in essence, all of the applications of short-lived proofs will be about deniability. Okay, so how do we actually construct this? It turns out to be pretty simple using SNARKs. It's really just a disjunction. So you take your original circuit, which can be any statement you want to prove, and then you add a second bit to the circuit, which verifies the VDF solution. And then the overall proof just proves that you satisfied one of those two things. And then it's really straightforward. The genuine prover just can prove the original circuit, so they don't have to worry about solving the VDF. And the forgery algorithm just solves the VDF, and then they don't have to worry about being able to prove the original statement. But of course, solving that VDF is really slow. So it allows you to forge, but at the cost of the slow computation. So we have a couple of other fancy constructions in the paper. Well, I should say, actually, we have one other SNARK construction and a whole bunch of non-SNARK constructions, which are much more efficient. But they achieve some notions of reusability. So you can solve one VDF and then you can forge as many proofs as you want. And it just adds a couple of extra pieces here. But I'll give you sort of the high level performance numbers here. So for the SNARK-based construction, it adds about 60 seconds of time to the prover. So basically, however long it takes to prove the original statement, add about 60 seconds, and that's how long it takes to do the short-lived version of the same proof. Yeah, that time goes toward verifying a VDF solution. So that's maybe okay for some applications. Might be pretty prohibitive for the email signature. If you have to do 60 seconds of work for every email that you're sending as a mail server, it's probably not going to work. So in the paper, we have some more specific constructions. So basically, this family of constructions, it doesn't work for any SNARK statement. It only works for Sigma protocols, which is a large class of zero-knowledge proofs. But you can see it adds a little bit of proof overhead, but the proving time is much, much lower. And then probably our best construction is specific to signatures. So the only thing you can do with it is a short-lived signature, not a general short-lived proof. But the performance is, it's pretty good. So this, if you think about doing an RSA signature, the short-lived version is basically twice the size. So you add basically one other group element and a really small amount of extra stuff. And the overhead for the prover is really small. So it's like milliseconds. So hopefully this is practical enough that you could roll this out for a DKIM mail server that's signing lots and lots of mail. I guess I'll skip this and just say, yeah, we have a bunch of different constructions. It was a really fun paper because we ended up defining like two new types of VDFs and coming up with lots of crypto tools to get there. But yeah, if I'll take questions on this part if anybody has any.
Hi, thanks for the talk. So,
sure.
Well, I have two questions.
All right.
The first one is that I saw something like a watermark via VDF in the previous slide. So, what's that?
It's kind of an interesting construction, actually. The original idea for a watermarkable VDF was that you could embed, so we were originally thinking about applications where you want to reward someone for computing a VDF. But once you've solved a VDF and if you try to post the solution to the blockchain, anybody else could try to take credit for it. So watermarkable VDFs let you embed some watermark into the proof that is difficult to remove. And you would embed the identity of the solver. So you basically solve the VDF and you put your identity in as a watermark. And that way no one else could claim that they solved it instead of you. So that was the original idea. And it turns out they're useful for short-lived signatures too. There's like one tweak, but basically you use the watermarkable VDF scheme and the watermark is the statement that you're signing.
I see. So it's kind of similar to a public key version of the VDF. Can I think that way?
It's not. I'm not sure. Yeah, like I said, I don't see the analogy there, but I think the public key version of the VDF maybe is a trapdoor VDF, where there's like a trapdoor that lets you solve the VDF quickly. I think the watermarking thing is kind of orthogonal feature.
I see. Yeah. Another question is about the trapdoor VDF. So does this construction require the VDF to have a trapdoor, or it can be constructed with a VDF without trapdoor?
Yeah, it does require a trapdoor. So normally for VDFs, the trapdoor is a bad thing. And people have thought about using class groups or a group without a trapdoor so that you don't have to do a trusted setup. For signatures, it's kind of clever. You basically treat the trapdoor as the signing key. And it's actually like used for a positive purpose. So you need a trapdoor. You can't do it with a VDF without a trapdoor, but that's actually what allows you to produce signatures efficiently.
Yeah, I see.
Yeah.
Those are my two questions. And
yeah, thanks.
Any other questions?
If there is no other questions on this talk, I would like to ask you about the Konig's work.
Okay,
if
sure.
that's okay.
Yeah. Go for it.
Yeah, sure.
Yeah.
I was just going to ask which signatures are supported for this short-lived signatures.
Oh, well.
Or can you support any signature?
Okay, so the efficient ones, the trapdoor signatures is basically only RSA signatures. This family can work with any signature that has a Sigma protocol, but that includes like DSA and Schnorr and Algamal signatures. Like almost everything else falls into this family. Anything else, like some really complicated signature scheme like Sphinx, you'd have to use the SNARK scheme and it would probably be pretty inefficient. But yeah, basically RSA, Sigma signatures, which is most, and then everything else.
All right, thanks. And can I ask the RS question from the chat? So I'll ask that. So we have a question from the Zoom by RS. So he says, thanks for the talk. My question is on, this is about the first one, by the way. My question is on application rather than cryptographic part. What are the advantages of this method compared with some solutions such as Cisco Umbrella or OpenDNS, in which filtering policies are applied at DNS resolver level?
Yeah, so what the question's getting at is that they have they have DNS resolvers that are filtered. So Cloudflare actually runs one. There's like a family-friendly Cloudflare DNS, which is how a lot of people set up filtering. They just direct their home network to use Cloudflare's like pre-filtered DNS. So we actually talk about this in our paper, and that's one mode that this can be used is to just prove that you're going to a filtered DNS resolver. I think the issue is that then the local network doesn't have any control over what's being filtered. So you sort of need you need two things. You need the client to trust that, like, if you're using Cloudflare's family DNS, you need the client to trust Cloudflare with their privacy. And you need the network to trust that Cloudflare's filtering is good. So if you don't have either of those, then you need to run the filtering locally. And we also talk about, there's a protocol called ODOH, Oblivious Encrypted DNS. And one of the applications in our protocol is, so Oblivious DNS basically adds a proxy between you and the DNS resolver to try to give you more privacy. So we actually implemented that and showed you could do Oblivious DNS and prove that you're going to a filtered resolver, and then the filtered resolver doesn't see you, so that your privacy is preserved. Yeah, so that it's a good solution, and we talked about it in the paper. Anything else on short-lived proofs? Oh, okay, yeah.
Okay, so is it possible that the adversary can distinguish between whether a private input it goes through this part of the circuit rather than the other part?
No. Yeah, no. So the zero-knowledge property ensures that you can't do that.
Okay, I see.
Yeah. Yeah, which is an important security requirement. Yeah, go ahead.
Okay, probably my turn now. So for the Connix paper, because that's already many years ago, 6 years ago. So from what I can remember, it was to use the idea similar to certificate transparency for messaging, where users could verify the authenticity of their own keys and potentially a history of all the keys. And normally with those constructions of the append-only log, we normally get the log n complexity in the verification.
Right.
And you mentioned that you are trying to use the zero-knowledge proofs to improve the efficiency of the Connix. And my intuition would be the way to use the zero-knowledge proof is to deliver the proof to the users on their key bindings for the entire history of what they have generated before.
Yeah,
right.
Yeah, so that's exactly, I was going to this slide because I think it shows like so this is like with Connix, the traditional model, every time a new digest comes out, so every time updates are published to the directory, you have to check again to make sure that your key hasn't changed in a way that you didn't intend. And then with kind of the new approach with SNARKs, you get one proof that basically can prove for a range of digests that your key hasn't changed in the whole set, right? So like with Connix, you have to check every single one, which leads to like the main performance bottleneck. But yeah, using SNARKs, you get one proof that everything is okay. So then if you go offline for a week and you miss like hundreds of updates, you can come back and efficiently catch up. So that's the whole goal of using SNARKs.
Yes, thank you.
Yeah. Sure.
So it's not about the construction in that paper, and so I have a question regarding that. It's the Merkle mountain range, which comes from a recent paper in Oakland last year. Is that that data structure helpful for this design goal, as the Merkle mountain range is kind of a linearly growing Merkle tree, and which can, even if the memberships are growing, and still it can generate a very succinct proof on the membership in this set. So is that data structure helpful? As I'm not sure if you know that.
Yeah, no. Oh, yeah, no. I know Merkle Mountain Range. I was going to say it's been around for a lot longer than since 2019. It's popped up in various versions for like a long time. But yeah, no. The difference is that if you have a bunch of versions of the Merkle mountain range, you would still the client would still need to check all of them. So it doesn't really get around this problem. It gives you an efficient way to prove that. I mean, the Merkle mountain range part would be about as you add users to the system, that's the Merkle mountain range. It's efficient to prove that you've only added users to the system. But if you're actually changing leaves, then the Merkle mountain range doesn't help anymore. Right?
I see. So this scheme also supports the changes of the keys.
Yeah, but I mean, you have to, because if users can't change keys, then it's not going to work for.
I see.
For messaging, right? Users change keys all the time. Yeah.
All right. So I think we don't have any more questions. So thank you everyone for tuning in.
Thanks. This was great. It was really good questions.
And thank you very much, Joseph, for the very interesting talks. Let's say 2 papers or 3 papers.
Yeah. I was maybe ambitious trying to talk about too many topics, but yeah.
Yeah, that's great. Thank you very much. So hope to see you everyone in the next seminar. And thank you again.